Oh, that sucks. Ah, that's too bad. Oh well. For those of you who are here, you got all of it. Okay, so we could write our vector function like that, right? The inputs are x, y, z, and we get 3 components, or we could write it like this. If you like this notation better, it's the same thing. Now, a lot of the times, the inputs or the parameters of this vector function, in this case x, y, z, they themselves are a function of some other parameter, maybe t, right? So x might be a function of t, y might be a function of t, and z might be a function of t. Okay, in which case, my vector function is absolutely, in its ultimate sense, is actually a function of this parameter t. So these expressions, Vx, x, y, z, is really Vx a function of t, I hat, a function of t, j hat, and a function of z, k hat. Okay? And when we're dealing with a position vector that traces out a curve, that's usually what we have. X, y, and z, the x, y, z coordinates everywhere on that curve are functions of t. That's what we did in the previous examples. Okay, and if it helps you, you can use the system concept, right, where your function is a box, and in this case, t is the input, right? And what do I get out of it? I get 3 components of my position vector. Okay, so that's all there is to it. Vector function, it's a function, you put in some values, you get a vector out of it. That's all it is. So let's look at how many examples. Now we've got one example. Right, and then we're, just like we did last year with scalar functions, we're going to start the calculus part of our course. So example 1, we've got a vector function r of t is equal to 2 cos t, 4 sine t, and t is the z component. All right, and as I've said before, it really helps in this course if you have a little bit of an imagination. I know for some of us engineers that's a stretch, right? But whatever imagination you have, try to tap into it. Try to visualize in your head what the curve looks like for this position vector r. Okay? So you look at what x is doing as t changes, you look at what y is doing as t changes, and you look at what z is doing as t changes. Okay? Z's pretty easy. It's just going to increase linearly with t. As t gets bigger, z gets bigger. Okay? What's x and y going to do? Well, whenever you see coses and sines, think circles, right? And we already, in the last day's lecture, we looked at the parametric equation for a circle, right? The x-coordinate was cos of t. The y-coordinate was sine of t. Well, that's what we got here too. So it looks like in the xy plane, this curve is a circle of some sort. Now, it's not a perfect circle. Why not? Well, look at the amplitudes of these cos and sine functions. They're different, right? Which means the x value, as t changes, what's the x value going to vary between? Can anybody tell me?
-2 and 2.
-2 and 2, right? Because cos is going to vary from -1 to 0 to 1, back to 0 to -1, back to 0 to 1, right? Cos goes from -1 to 1. Multiply that by 2. X is going to go from -2 to +2. What's y going to do?
-4 to 4.
-4 to 4, thank you. Exactly, right? Because sine, just like cos, goes from -1 to 0 to 1, back to 0 to -1, back to 0 to 1, back to 0. Multiply by 4, we go from -4 to 4. Will x be at -2 at the same time t as y is at -4? No, because sine and cos are 90 degrees apart, okay? And that's what gives us a circle as t changes. So what does this thing look like? Well, this is actually going to be, it's not a perfect circle in the xy plane, it's more of an ellipse, right? X is going to go from -2 to 2, and y is going to go to -4 to 4. So it won't be a circle, it's more like an ellipse, okay? And if I draw it, it's going to look, oh, this is going to be hard. So x is going to go from -2 to 2, something like that. Y is going to go from -4 to 4, something like that. When t is equal to 0, where does this curve start? When t is equal to 0, cos of 0 is 1. It's going to start at an x value of 2 and a y value of 0. So that's here, and a z, so it's going to start right there when t is equal to 0. Okay, it's going to go counterclockwise. So it's going to do something like right, because as t goes on, z gets bigger. Oh, that's not bad. That's not bad. I even impressed myself that time. Okay? So if t starts at 0, it's right here. And as t increases positively, we go around this elongated circle and z, and we go up with z, because z is just t. It's initially 0, so here z is equal to 0. Obviously, everywhere else on this curve, z is not 0 anymore. And if I drew the position vector at any particular point time in t, let's say for this point right up here, the position vector always starts at the origin, like that, right? So that would be my position vector r at time t when I'm at that point. All right. How are we doing for time? Front row, are we still good? 9:32, thank you. Okay, so those are vector functions. That's it, okay? So because they're functions, we can do calculus to them, right? You knew calculus was coming eventually. This is multivariable calculus. So we're going to start calculus now. Because they're functions, we can take derivatives of them and we can take integrals of them, okay? Now the good thing is they're no more difficult than finding the derivative or integral of a scalar function. It's just you got to do more work because there's more components, right? So we can find the derivative of a vector function. Okay, I'm not a mathematician, so I'm not really much into proofs and all that sort of thing, and formal definitions, but we'll write this one down just to jog your memory. I can take the derivative with respect to the parameter of this function t of my vector function r, okay? And I could also write it like this, use the prime notation. Hopefully you remember that from last year, right? So either one of those means the derivative of this vector function with respect to the parameter t. And it is a limit. Okay, so just like last year where y is a function of x, r is a function of t, right? The derivative is the difference in the vector function as t changes just a little bit, divided by that change. So that's the formal definition of a derivative. It's just exactly the same as with a scalar function. Okay, well, how do we find the derivative of a vector function? Well, let's say our vector function r of t is equal to some function x of t, some function y of t, some function z of t, right? So we've got three expressions representing the x, y, and z components of the vector function, and each of those expressions is a function of t. Well, then the derivative of the vector function with respect to t, first of all, what do you think? Does it give you a scalar or does it give you a vector? When I take the derivative of a vector function, will my result be, will the derivative be a scalar function or will it be another vector function? What do you think? Just guess.
Vector.
Vector, right? Yeah, that's the first thing a lot of people say, right? And exactly, you take its derivative of a vector function, you get another vector function, right? Just like when you take the derivative of a scalar function, you get another scalar function, okay? And what do you think the derivative is? Well, it's just the derivative of each of those components. It's really simple. I get another function, vector function, and the first component is just the derivative of that first expression with respect to t. Derivative of the second with respect to t. Derivative of the third, the z component, with respect to t. All right, so it's that easy. No big deal. So all the rules of taking derivatives are the same because, you know, what is this function here? Well, it's a scalar function of t. You all can find the derivative of that already. This is a scalar function of y. This is a scalar function of z. That's why I said it's the same as last year. It's just you got to do 3 times as much work because there's 3 different expressions you got to take the derivative of. But all the rules are the same. Everything's the same as last year. Okay, so that's the good news. I guess the bad news is that you got to remember all your derivative and integral rules from last year, right? Hopefully you didn't think that you would never use those again, obviously, right? You're going to use them for the next 4 years. Well, years 3 and 4 probably less so, but we still need them in second year for a lot of stuff. So if we've got that vector function and we want to find its derivative, I just take the derivative of each of those 3 components of that vector function with respect to t. So hopefully you remember that the derivative of cos is what? Negative sine. So the first one is negative 3 sine t I hat. Derivative of sine is cos, so plus 3 cos t j hat. And the derivative of t squared with respect to t, obviously 2t, k hat. Okay, so that's it. You just take the derivatives of the 3 expressions. Now those expressions may be complicated expressions, and finding the derivative, you know, you're going to have to use the product rule and the chain rule and all those rules you learned last year with scalar functions, with calculus, with derivatives. They all apply here too, okay? So if r of t, if this vector function represents a position and I take its derivative, what would that represent? When you take the derivative of position or displacement, what do you get? Velocity, right? So really r prime of t, I could interpret as the velocity along that curve, right? And if I take the derivative, I shouldn't write v prime, sorry, velocity. And if I take the derivative of velocity, what do I get? Acceleration, right? So what would I get there? Well, what's the derivative of sine? Because I'm taking now the derivative of this, the velocity. Derivative of sine is cos, so I get negative 3 cos t I hat. Derivative of cos is negative sine, so 3 negative 3 sine t j hat. And the derivative of 2t would be t. So that would be my acceleration vector now along that curve that is described by the position vector r. Okay, and if I asked you, well, what's the speed of a particle traveling along that curve defined by the position vector r? How would you find that? Speed. How is speed related to velocity? Magnitude, right? So the speed would be equal to the magnitude of my velocity vector, which would be what? Here's my velocity vector. How do I find the magnitude of that? This squared plus this squared plus this squared square root. Excuse me. Well, I would get 9 sine squared t plus 9 cos squared t plus 4t squared, right? Would that not be the sum of the squares of these three components here? Okay, which would be equal to 9 plus 4t squared, right? Because sine squared plus cos squared is 1. Take the 9 out. 9 plus 4t squared. Okay, so again, it's just an example. These vector functions can represent physical quantities. Obviously, that's how we use them to be of benefit to us. Okay, so there are a few, let's just remember the rules of differentiation. We've got the rules of differentiation for the individual scalar functions that make up a vector function, but we can also talk about the rules of differentiation of the vector functions themselves. For instance, what if we're taking the derivative with respect to t of a scalar function times a, let's use the same thing, u, times a vector function. So what if we've got a scalar function multiplied by a vector function, and we want to find the derivative with respect to t of that product? Well, that's kind of like the product rule, right? And if you don't remember the product rule, it's the derivative of the first times the second plus the first times the derivative of the second. Or if they're both vector functions, same thing. 1 times the derivative of the second plus the second times the derivative of the first. Okay, so that was the product rule. If we have two functions added or subtracted, well, it's just the addition or subtraction of their respective derivatives. Okay, I misspoke here. This is intentionally a scalar function times a vector function. It's not actually quite the same as when these are both vector functions, because if they're both vector functions, how many types of multiplication do we have if you're dealing with vectors as opposed to scalars? Two, right? The dot product and the cross product, right? When we're talking about two vectors, there's two different ways to multiply two vectors together. We can take the dot product or we can take the cross product. So we have to specify that if we're dealing with two vector functions. So really the product rule for two vector functions, if it's the dot product of these two vector functions, well, it's just the same thing. The derivative of the first dot the second plus the first dot the derivative of the second. So it's the same product rule. And thankfully, Cross product is the same thing. So in actuality, I didn't misspeak earlier. It's the same thing, but you just have to be cognizant that it's either a dot product or a cross product. Same rules, but when you're dealing with vector functions, it's usually more work, right? Yeah, we're close to time. Okay, let me just write the last one, which is the chain rule, because it's very important, and we'll end there. So the derivative with respect to time of a vector function and the parameters of the vector function themselves are a function of some other parameter. Okay, so my vector function u is a function of x of t, where x of t is a scalar function of some parameter t. Then that is going to be the multiplication, the derivative of my vector function with respect to x, that function x, times the derivative of x with respect to t. That was the chain rule. You remember the chain rule from last year, right? Okay, and then there's one more there, which I'm not going to write down. It's the derivative of the triple scalar product, or pardon me, of the triple product, which is one vector function dot a second vector function cross a third vector function, and it's a long drawn out thing there that you can look at in the notes, okay? All right, so we'll look at some examples of that next day, and yeah, that'll be it for that. So we'll see you Friday. Thank you for letting me know about the time.